This conference will now be recorded.
And you can, the outside air from system will be TFA unit, that's fine. And the cool sizing ratio, now you have to set it at 1. You come to unitary power and you enter this EIR, which is 0.25. Okay. Now we go to HVAC system 2. We do the same thing. Change it to packaged variable volume. Go to fans. Change it to 0.007. And outdoor air is from TFA unit, that's fine. Go to cooling. Change the cool sizing ratio to 1. Unitary power, change it to 0.25. So that's about it. That's the changes you have to make. And sometimes what happens is they also provide the outdoor units capacity, which may be slightly lower than the sum of entire indoor unit. Okay, so for example, all the indoor units, if you sum it up, it comes to 3,36,000. All right, but the outdoor capacity, outdoor units capacity might be about 3 lakh only, slightly smaller than the sum of this. The idea behind this is not all of them will heat peak load simultaneously. So that is one of the main concepts behind different sizing. Okay, so when you sum up all the indoor units, it will not be equal to the outdoor unit capacity. So if that is given, you can actually enter it under cooling, the total cooling capacity. Right. Those fans were variable speed, that's fine. Okay. Okay, that's about it. And in water side system, okay, this is only going to the TFA unit. TFA on it also will change it to a simple package single zone. The control zone being TFA zone. Okay. One of the things is that you have to specify is the fan power for this TFA unit and the flow parameters. So if you specify what was the total flow rate and the design kilowatt per CFM, so it will automatically then give whatever air is required, fresh air is required to the other systems, and it will also consume the power as envisaged. So we were getting about, I think, not sure if summary. Okay, yeah, it's enabled. We were getting the design outside air as system 153 and 1673. So 153 plus 1673, we get 1826 CFM. So let's say 2000 CFM. Okay. So we'll say 2000 CFM, and the fan power maybe, let's say 0.5 kilowatt. So 0.5 divided by 2000. 0.00025. So 0.00025 is the fan power, and flow parameters will say the design CFM is 2000 CFM. Okay. So this is individually, it has its own packaged this thing. Okay, so we have one doubt. Evaporator TR is equal to condenser TR minus compressor TR. I'm sorry, like evaporated TR is equal to condenser TR minus compressor TR. No, I'm not sure how we derive with this calculation. Obviously, condenser tonnage will be higher, no doubt.
Sir, I'm here. I only posted the question. Can you hear me, sir? Hello?
Sorry, yeah.
Sir,
Yeah.
yeah. Sir, actually, during energy audits, we used to assess the performance. We assess the get the tonnage either from evaporator side or from condenser side, whichever is possible. So while we get the tonnage from condenser side, it should be higher because it is the combination of compressor work and the condenser heat dissipation. So the sum of this tonnage will be equivalent to the heat which is taken by the evaporator in the interior side. So this is how we balance the system. So once we get the tonnage from condenser side, we used to minus the compressor power, which is in kilowatt, which you can measure using a power meter or something. That we divide by 3.51 because 3.51 kilowatt is 1 kilowatt is equal to 1 ton, 1 TR, as per our calculations. So that way it should be higher, right? This condenser.
No, 1 second. Compressor TR, when you are calculating, you are only measuring the electrical input.
No, we are measuring the electrical input and we will be dividing the efficiency. We will be multiplying the efficiency and we will motor efficiency also. Then we will get the input to the compressor.
So what about the COP?
That's what we divide this using 3.51.
You just get the tonnage then.
Yeah,
what
yeah,
about
we'll
the
get
COP? What about the compressor COP?
COP is the this one, the condenser TR what we are measuring now. So we will divide the cooling watts. That TR will be multiplying by 3.51, and we will be getting the cooling watts. So that divided by the electrical input. So that will, if in case of small ACs, it will be measuring the energy efficiency ratio ER, and in case of larger systems, it is COP.
No, okay. Let's assume whatever you are doing is right, but like, what is your ultimate goal in
Sir,
this
in
scenario?
one that one somewhere you entered the condenser TR, right? Then you told that is less. That's why this doubt came.
No, condenser will. Sorry, hang on. See, the outdoor unit. This is outdoor unit. I'm talking about our VRF system, not a chilled water system.
Yeah, here also the outdoor unit will be holding the condenser, right?
Yeah, it's a condenser, but condenser is sized less because
Then
not all of them hit.
then its TR should be high.
Why do you think so?
Because it is including the work done by the compressor also.
No, you're not understanding system balancing. See, if I have like, will all of this is my peak load. Will all of this hit at the simultaneously? That is my question.
Okay. This is the maximum value. Okay, fine.
Yeah.
Okay.
Right, and that is number one. And when we come to chilled water based system, obviously, yeah, the cooling tower, okay, or the heat rejection size is higher. One of the main reasons is that water is the transfer medium over here, and the temp delta T, delta T that you achieve, right? I hope you are understanding. The delta T that you
Yes,
achieve
yes,
here
sir.
is significantly less than the evaporator side.
Yes, yes.
So that is why in chilled water case, in case of chilled waters, the tonnage is higher.
Okay.
Whereas here it is the refrigerant. In case of VRF system, it is the refrigerant which is going to the condenser, and the delta T is almost, you can say, approximately almost equivalent, if not higher. Okay, so in VRF systems, our main thing is that we are looking at this thing. Either it will be sized similar to the total capacity, or it will be slightly less. So that's something you can rightly say. Diversity factor is taken into account.
Okay, sir. Here, what is the sum what we got? This 96,000, and we got around 3 lakh, right? 3 lakh.
3,36,000. Yeah.
3 lakh
So this
36.
is
Then
28
that,
ton.
okay. Then condenser PR, how much should be?
Maybe around 25 should be okay.
3.5.
25 ton.
25. That's what where there the compressor work is not accounted.
Uh, no, this is the outdoor unit. I'm talking about the outdoor VRF unit, right? So that capacity, that is the
Okay.
total cooling
Okay, you
capacity,
are
25
giving
ton. Hmm.
the tonnage capacity of the condenser alone. Okay, fine. Then it is fine. Okay. Understood, sir.
Right. Yeah. So when you're specifying TFA unit, yes, you have to consider 100% diversity. You have to give maximum full fresh air. Okay. Right. Uh, that's one. Where were we? Okay. So TFA unit, we specify the fan power and flow parameters we have specified. So that's that. And okay, I think we are ready for simulation, except that we have to delete these. As you can see, nothing is connected, to the CSW loop. So we'll have to delete this entire loop and everything. So we'll start deleting one by one from bottom up. Otherwise, what will happen? The chiller will not, the simulation will not run. Okay. Okay, it is connected to TFA unit. So the boiler also needs to be deleted. So anything on which there is no load, either it is cooling tower or chiller or boiler, would have to be deleted. Otherwise, the simulation will not run. Okay, and this one. Okay. So now we are ready for simulation, and I think we have entered all the details. So let's see. Okay, so we're getting 486 hours in throttling range. Earlier, in the baseline case, I think, which we also need to run once again because there was an issue. Let's open that also. Here, the only thing that we had missed was this should have been 0.7. It shouldn't make too much of a difference if we run the simulation now. If we go to BPU, okay, yeah, it is greater than 300. So we'll have to reduce this a little bit more. Okay. Sys2 is all right. System 1. L1, we need to provide a slightly higher load. So because of the rooftop, it is needing slightly higher airflow. So we can probably make it 1.2. Okay. I think that should take care of the throttling range. Okay, let's come down to 61. Now, if it comes down to 61, I have to make sure that this is between 16. So my baseline is 61. So plus 50 is 111, and 61 minus 50 is 11. Okay, so it should be between 11 and 111. The throttling range in my proposed case should be between 11 and 111. Okay, plus or minus 50. So accordingly, I have to see what the problem is over here. It's on level 1. Okay, that being on the top floor. So maybe we can try a high SRI paint. Let's look at that. On the roof. Sorry, this is the baseline. On the roof, maybe we can try high albedo paint. So maybe reduce this to 0.3. And let's see where it goes from there. Okay, so this is the proposed case. As you can see, it has come down significantly. And if we look at the PU report, 32. So I'm in my target range. This is 61 and this is 32. Absolutely perfect. And if you look at the energy usage, the first thing is I have to check my miscellaneous equipment should be equal in both the cases. Let me in fact, okay. So the top one is proposed, the bottom one is baseline. Okay, as you can see, 61877, 61877, both are equal. Miscellaneous equipment should be equal in both the cases. Lights, obviously, we are getting significant amount of benefit. Then space cooling is okay. There we are. Space cooling is mainly the compressor work. Okay, that's all right. And domestic hot water is equivalent. External usage is equivalent. Although you can get some savings in here also in external usage. But overall, as you can see, this is the baseline, which is higher, and this is the proposed case, which is lower. So obviously, we are now KSECBC compliant. Okay, so that's how you have to do the modeling. So in this case, your recommendation will be to just apply high albedo paints on the roof, or the other option will be to slightly, as you can see over here, the top floor, you see is similar to the ground floor and middle floor also, which is not the case. This will be slightly higher, maybe half a ton higher. In reality, it will be about half a ton higher or 1 ton higher if it is, similar to a typical flow. So that's how you model VRF system. And yeah, so these are the maximum systems you can encounter. It will be either a chilled water based system or a VRF system, and this is how you can actually complete the entire process. Of course, there's one more thing that I've forgotten, which is basically you have to rotate the building also. Okay, so for that, what we'll do is we'll go to baseline, tools, parametric runs, and okay. This is baseline 90. You have to rotate. So we create a parametric component, which is basically so all the parameters which you find in the background, you will also find it in parametric runs. So what parametric run does is it creates another file and overrides whatever parameter you have given over here. So this will come in building parameters, I believe. Yeah, build parameters and azimuth. So ours we had given minus 43, the original. So we can give plus 90, so that's 47. Again, create another parametric run. This is baseline 180. And parameters, azimuth, and some plus 90, 137. Create another parametric run, baseline 270. Create parametric component, parameters, azimuth, and this will be plus 90, 227. Okay, click on done, and you simulate all of them. And you can just go to summary, and on the bottom under reports you will have under parametric runs annual end use summary, and you can just copy this, copy selection, and here you can just paste it. Then you have to replace the comma by blank. Oops. There you go. And in the proposed case, we had 46, 5. Okay, so you can also find out the consumption over here, the EPI. So for that, you need to give the area of the building, which you can actually find out in here. Summary of spaces. So the total area is 433,314. Okay, so this is the EPI. The baseline is the average of these four, and this is your proposed. This is the EPI. The throttling range in baseline 0 was 61, and in proposed case we had 32. Okay, and the EPI ratio is this divided by this. So the EPI ratio, it is required in ECBC 2017, not required in as per KSECC, but probably they might change the rules sometime and ask for it also. But more or less, this is how this is your final submission. Okay, so you can say, yes, this is compliant. The reasons being that an annual energy consumption of proposed case is lower than baseline. The throttling range, the difference between the two is within plus or minus 50, and therefore it is ECBC compliant. So that's basically it. And any doubts you have, you can probably ask. But more or less, I've kind of shown everything which you will require for your submissions. Any doubts, any general queries, you can always ask. If there's anything that you think I might have missed, then yeah, please let me know. Okay, so can we go through the TFA modeling once more? Yeah, sure. So TFA, you specifically need to model in your proposed case. So when you are modeling TFA, the first thing that you need to do is create a dummy space, which will be specifically for a TFA. After you can create that dummy space in building shell, you go to air side, and there you create a zone, TFA zone. Okay, and you put in whatever thermostat schedules you have to put in. and then you make a system, whichever is your topmost system, that should be converted into TFA, and everything originally in that system you move it down to somewhere else. Okay, but it is always the hierarchy because the bottom systems are drawing air from TFA. Okay. So TFA unit, when you model, all you need to do, make sure is that you have this fan power, which is basically kilowatt divided by CFM, and you enter the flow parameters. So that's also something that you can actually check when you go to SPA, and here you can see the power demand is 0.5 kilowatt. So I think that is what we had entered. Remember, so 0.5 divided by 2000, 0.00025. Yeah. Okay, so you can see the power demand, it is exactly matching. And here under the, so this variable speed should ideally be only there if it is actually modulating. If there is a damper on the TF unit, only then you should put it as variable speed. Otherwise, this will be constant volume because the fresh air has to be supplied every minute. Okay, every minute you have to supply some amount of fresh air. Apart from that, sometimes in conference rooms they provide DCV return sensors or demand control ventilation. What that is, you can actually look up in your Google search. But basically what that means is on outdoor air, you provide demand control ventilation from here. That's DCV return sensor. So whenever there is low occupancy, what will happen is that the DCV sensor will moderate the fresh air and it will reduce the amount of fresh air that it is introducing into the system or into the space. This is mainly given in conference rooms where suddenly the occupancy can increase and maybe after some time the occupancy can decrease. Just a second. Okay. So DCV return sensor, this is demand control ventilation return sensor. This is how you can put DCV return sensor. This also leads to some savings, specifically when there is a conference room. And then obviously, if you want to take benefit of this DCV return sensor, you need to have a schedule which, wherein, for example, there is a schedule. Let's go to the zone occupancy. As you can see, 11 to noon. Here, the fresh air requirement will obviously be low. So if you give the DCV return sensor, you can actually reduce the energy consumption also. So let's give it a try. Under outdoor air, you have DCV return sensor for both systems. And let's simulate it and see what the resultant output is. Okay, so you see there has been slight reduction. Earlier we had 486. You can see 486,505 was our earlier energy consumption. Now when we included the DCV sensor, we have about reduction of about 2000 kilowatt hour. Okay, that's also one of the methods, but you can get too much energy savings. The reason being, as I said, it's just that 1 hour. This is the baseline. Oops, sorry, the proposed. So it's only that 1 hour that we are getting the benefit. Okay, so that's why the dampers are modulating and they are reducing the energy consumption. So that's basically it about TFA unit, and of course, for the systems that are connected to TFA unit, the outdoor air from system should be, TFA unit for those systems. Difference between HAP and eQuest, there's no difference. Technically, it's just the graphic user interface that's different. And HAP is paid software. Obviously, you have to purchase it. eQuest is free. And HAP, the user interface, it's you have to, in HAP you have to give all the details like the wall area, the roof area, the glass area, the orientations. You have to specify everything in HAP. While in eQuest, what you're doing is you're actually taking a CAD drawing and you're building a 3D model. But HAP, you will have to manually enter all those details. By details, I mean specifically the wall area, roof area, window area, and the space area and the volume. So you'll all have to measure and enter it into HAP. So that's one of the major difference between HAP and eQuest. And of course, the simulation wise, the engines might be slightly uh, different, but both of them are quick. Now, even HAP is also user friendly. eQuest is also user friendly. It depends, what you're more comfortable at. If it's a very small space, probably you can just go by HAP. Because the small spaces, you have to measure it. Yes, you can do curtain walls in eQuest. So curtain walls, basically what it means is you have to understand what curtain walls are. You have, um, let's say the floor to floor height is 12 feet. In 10 feet, you will have glass. In another 2 feet, you will have glass, which is basically, which we call spandrel panel. You'll have glass along with insulation. So that will technically be considered as wall. So it will be 10-foot glass and 2 feet of wall. So you will model it as 10 feet of glass. Okay. Yes, for VRF and split systems, unfortunately, they do not have a separate, an inbuilt provision for fresh air. You have to provide TFA. Whereas in air handling unit, it comes in with in chilled water based systems. The AHUs have their own outlets for fresh air. So in those cases, TFA is not required. But if you want to provide TFA, you can still provide. But for VRF and split, it's definitely required. You can't change units in eQuest. In eQuest, it is IP unit only, metric unit. There's no SI unit in eQuest. Design builder, obviously you have to get used to the software. For design builder, the backend engine is Energy Plus, which takes a bit of more time when you're simulating, and it can obviously throw up some errors. So it's all about how much user friendly, and of course, uh, Energy Plus is accurate. The accuracy level of Energy Plus is comparatively higher in comparison to eQuest. But yeah, these are the major advantages eQuest has. One is that it is very quick and it is free. Ideally, no, you should not play around with throttle range, but if that's something that, because the rules explicitly do not say that you have to or you are barred from changing the throttle range, you can actually change it. But that's kind of a last resort. You have to see why you are getting the throttle range in the first place. Most of the times, it's basically your systems are undersized, or you have occupancy, and during that time, the HVAC is not running. That could be one of the possible reasons. But if you have set everything correctly, you will not get the throttle range. Or I mean unmet hours. Okay, any more questions?
Participants, do we have any other questions? We can wind it up.
What design inputs are typically fed for modeling PV systems? I would suggest, don't model PV system in eQuest photovoltaic system. You can just use the NREL's website to get your output that is much more reliable, and you can just subtract it from whatever load you got here. Whatever you get here, just subtract it, the PV systems output from NREL's website. What kind of worked out examples are you saying? Do you mean regarding a worked out example of a project?
Just to practicing for practicing engineer beginners, whether we can have for request.
No, I'm not aware of any such tutorials. Maybe EV cell can maybe later on. If they have time, they can, or I'm not aware, unfortunately. I'm sorry.
Sir, I think tutorials like this means we are conducting webinars. They are a kind of tutorials only. and recordings will be provided to the participant later on. So it is one of the simplest way we are doing it. If we are going to search for an equest tutorials, this is much better version, to be frank.
Yeah, absolutely. I mean, that's yeah. Ultimately, I mean, irrespective of whatever tutorials you take, you have to go for live projects. Only then things will become clear. Only when you sit in front of client and when they ask you questions, only then things will become clear. Otherwise, it's you have to go into live projects, quite frankly, yeah, rather than the tutorials. Okay, so I think we can wind up here.
Yes,
Sir,
okay.
can you tell how solar PVs can be model? Suppose now installation solar PVs are done on building top. Can you give an idea how they will be modeled?
Yeah, solar PV. That's what I said. Go for NREL website. Can't remember what exactly it is. Uh,
Sir, you will get the irradiation data.
Solar calculator. Yeah, just search. Yeah, PV watts. Just use this website and here you can just enter whatever. Let's say. What should I say? Delhi. Let's say. And then it'll automatically search everything and it'll generate and go to system inputs, and this is much quicker, and go to results. Okay, whatever you want and it will give you the results, plain and simple. So this is much more faster. You don't have to model it in equest. Can we just take some AutoCAD drawings and do simulations? Yeah, obviously you can. Absolutely, you can take the AutoCAD drawings and do simulations in practice. But who will assess the work? You'll have to find
Sir,
someone.
one doubt. Sir, in this, how the area is assumed, this meter square, NREL
Sorry.
website, this NREL website which you have displayed, no? This irradiation data we will get for a region. How this meter square is assumed? Are we giving the area?
Area for what?
Yeah, area for kilowatt. This kilowatt it is calculating, right?
You have to give the kilowatt. For that, you can just use a thumb rule. It's 10 square meter per kilowatt.
Yeah, that we have to enter in this website or what? They have taken
No,
it.
you don't have to. You don't have to enter. You don't have to. Just enter the system size, maybe 1 kilowatt or whatever, 10 kilowatt. Area is assumed,
Okay.
square meter per. That's just thumb of rule.
Okay.
Rule of thumbs. Sorry. Okay, so I think we can wind up now.
Okay, sir. We have come to the end of this webinar. Hope all of you had a great session today. I thank our master trainer, Mr. Kumar Biplab, on behalf of EEB Cell Energy Management Center Kerala, for spending his time and sharing this valuable knowledge. Hope would be useful for all of you. I would also thank you all the participation for your participation. Before you leave, we would like to know what you thought of this webinar, and therefore we would like to ask you to fill a short feedback form provided in the chat box as soon as possible so that we can improve our webinars in the future. Those who haven't filled it yet, please take out some 5 minutes to fill it up. And for others who have filled it up, thank you for your response. You will also receive an email containing a link of this training section once we upload it, so that you can watch it again and at a later time and practice by your own. Certificates will also be provided to the participants later on. If you have any doubts, please mail it to us or you can call at the EMC. Thank you all for your attention and we'll see you next time. Have a great day. Thank you, sir. Thank you all.